Reductions are carried out using reducing agents. As we can see, we're going to look at oxidations and reductions. Alcohols are important in the synthesis of aldehydes, ketones, and carboxylic acids. All of these functional groups can be converted by simple oxidation and reduction reactions. Remember, oxidation is loss of electrons, reduction is gain of electrons. But we also need to look at carbon. If it gains an oxygen, this is oxidation. And if carbon gains a hydrogen, this is reduction. So there's a number of factors we need to consider. So let's look at reductions here. Reductions are carried out using reducing agents. During these reactions, hydrogen atoms are added to the oxygen, and oxygen is either lost or its content is reduced, its percentage. Reducing reagents include sodium borohydride, which we've seen before, lithium aluminum hydride, which I mentioned earlier on in one of my lectures online. We can also use lithium aluminum triterbutoxyhydride, lithium aluminum triterbutoxyhydride. You can see that it's sterically hindered, so it's going to be less reactive. We're also going to use DIBAL, which is diisobutyl aluminum hydride. You may also see it written this way, DBAH, diisobutyl aluminum hydride, which is used at minus 78 degrees C. So lower temperature means it's going to be more selective and less reactive. So the diisobutyl aluminum hydride looks like this. Two isobutyl groups and a hydride source. Again, it's a reducing agent, minus 78 degrees C, dry ice and acetone. Now, things to consider. Ketones are reduced to secondary alcohols. Aldehydes are reduced to primary alcohols. Okay, let me repeat. Ketones are reduced to secondary alcohols. Aldehydes are reduced to primary alcohols. Carboxylic acids are reduced to either aldehydes or primary alcohols, depending on what's added. So let's first look at primary alcohols and their reactions. Okay, here's our primary alcohol over here. You can see that aldehydes are reduced to primary alcohols. We can either use the lithium aluminum hydride or the sodium borohydride. I do want to emphasize particularly that if we use the lithium aluminum hydride, we're going to use ether followed by HCl, whereas we use the sodium borohydride, we can use ethanol or methanol followed by HCl. And that's going to be important because this is the reagent we're going to use in the lab when we carry out our reduction of benzophenone. So these are our reducing agents to convert aldehydes to primary alcohols. In order to reduce a carboxylic acid to an aldehyde, we can use either DIBAL at minus 78 degrees C, or we can use the lithium aluminum triterbutoxyhydride. As I mentioned, the triterbutoxy group is sterically hindered, which selectively allows us to only reduce to an aldehyde, and the DIBAL is at minus 78 degrees C again, sterically hindered, lower temperature to the aldehyde. And then finally, we can see that the carboxylic acid is reduced to the primary alcohol, either using our lithium aluminum hydride in ether, followed by HCl, or the sodium borohydride in ethanol, followed by HCl. So it's important to know which solvent goes with which. In all of these cases, you'll notice we add the HCl to protonate the alkoxide anion intermediate. On the lower part of this page, we can see that the ketones are reduced to secondary alcohols. Either the lithium aluminum hydride in ether, followed by the HCl, or the sodium borohydride in ethanol, followed by HCl. Both of these facilitate reduction of the ketone to the secondary alcohol. So both are possible, both can be carried out. Okay. Now, take a look at the next page. We can look at how this reduction takes place using the lithium aluminum or sodium borohydride. Okay, we should recognize that the sodium borohydride, the lithium aluminum hydride are sources of hydride ion. The hydride is going to come in and attack the most electrophilic center, which is the carbon of the carbonyl. Okay, we know that it's more electrophilic because the oxygen is more electronegative, and as it attacks that center, the electrons are going to move up to the oxygen to form this intermediate, which is our alkoxide. Okay, all the groups are the same. We've just added the hydrogen and converted our sp2 center to now an sp3 center. We got our alkoxide with a negative charge. Then we add our acid, generally HCl, about 3 molar. The negative charge comes in, picks up the proton from the acid, in this case our hydronium ion, and so we produce our alcohol. As we can see, aldehydes are reduced to primary alcohols, ketones are reduced to secondary alcohols. That's going to be important to know because we're going to see that throughout the semester. We're talking about alcohols. We're also, next topic is going to be aldehydes and ketones. Important transformation.